So next time I'm going to talk about some word problems dealing with integrals. And an example of a problem like this would be this one on the board. The marginal cost of manufacturing X yards of fabric is given by this function in dollars per yard. Find the increase in cost if production is raised from 2,000 to 4,000 yards. So you imagine, okay, you're given a derivative. We want to find the antiderivative, we want to take the integral. But what are we really doing? This thing has a name. It's called the Net Change Theorem. And the statement of the theorem is very simple. It is the integral of a rate of change is the net change. Okay, so if you watched the videos by 3 Blue 1 Brown, the Essence of Calculus 1, or the other one about fundamental theorems of calculus, he used the problem of a car on a road, and you know the velocity, and we're trying to find the distance. So I'll do one similar to that as well, but this is a different problem. I mean, it's basically the same thing, but here they're giving you a rate of change of this called, as you remember, the marginal cost, the change in cost as a function of the number of units produced. So you know it's a rate. First of all, they kindly told you it was C prime, and it's dollars per yard, so you know that there's a rate of change. If I want to find the increase in cost of production, or the change, or the net change in production, right? What I want to do is I want to take my integral of the function of the rate of change, so 3 minus 0.01x plus, you get all these zeros here, 5 zeros, right? That's my function. I'm going to integrate that from 2,000 yards to 4,000 yards, okay? So the net change then is going to be, this is C prime, it's going to be C at 400 minus C at 200. So I'll write that. That's what we're actually going to do. Now, when I integrate this, it's pretty straightforward. I have 3x minus 0.01 x squared over 2 plus this thing, x cubed over 3, and I'm going to evaluate that from 2,000 to 4,000. But I meant 1,000. And I'm not going to bore you while I plug this into a calculator or whatever. The answer is actually 58,000. So you can plug them in and check that as well. So this is going to be the increase in the cost of production. Okay? But really, all we did, we were given a rate of change. In this case, it was a rate of change in cost, but it could have been, for example, velocity or any other calculation, anything, right? The rate at which water is leaking out of the bucket. There's various problems that are set up this way. And all you need to do is take the integral. Now, it's important to point out, why is it called the net change theorem? Because it gives you the net displacement, right? Sometimes things can go up or down. Our functions, sometimes they go up and down, right? So to get some idea of that, let's talk about a velocity problem. This is a particle moving on a straight line. a particle moves on a straight line, so you can think of the car going straight back and forth or whatever, and we're given the velocity. What do I have? 3t minus 5, something simple, right? And what we want to do is find the displacement from t equals 0 to t equals 2. Now, previously in Calc 1, they gave you the position and you had to take the derivative to find the velocity, take the derivative again to find the acceleration. Now we're going backwards, right? They give you the velocity, and what you want to do is find the displacement. So I'm just going to integrate from 0 to 3 using my Net Change Theorem. Okay? So this, again, is easy enough. Okay, so this is going to be, oh, what were the units? I forgot to write down the units, darn. It is in meters per second. That's important, right? You don't want to forget our units. Okay, so this would be 27 halves minus 30 halves. So, minus 3 halves. Okay. Wow. So, it's moving backwards, right? Is what you're supposed to figure this out. Couple things before I go on and talk about that a little bit more. I want to point this out. This, I didn't evaluate at 0, right? Because both of these are minus 0, minus 0. I probably should have written it because you want to keep that in mind. It's not always 0 at 0 when you're evaluating integrals. So it's a common mistake is to just, when the lower limit is 0, you just forget it. Don't forget it. I mean, you don't necessarily have to write it if it's going to be 0, but do it in your head. Make sure not to forget to evaluate at that lower limit, because not all functions are 0 at 0, right? They're 99 common with no common term. Okay, anyway, so now what do I mean by this? What's actually going on here? Okay, so let's think about it. This is a line, right? But if I draw this line, 1, 2, 3, 4, 5, it's here. 1, 2, 3, right? So somewhere here. So that's not a very accurate graph, but it gives you the idea. This is the velocity. Now what it means is that on this, before this point, right? This point, which would be at t equals 5/3 seconds. Before that point in time, my velocity is negative, meaning my particle is moving in the negative direction. So if I think about my line here, I'm starting, say I start from, we're going to call it the origin, right? Wherever my starting point is, for the first 5/3 seconds, I'm going back this way, right? Because my velocity is in negative direction. And then, for the rest of the time, I'm going forward. Now, I don't actually probably end up going all the way there because it kind of goes this, right? Because my was negative in the end. So it looks like I didn't make it all the way back. But if instead of going to 3, maybe we went to 10, right? This particle would keep going, right? And we would see it there. However, what this gives us the displacement, right? It gives us the position at, what this is, position at t equals 3 minus position at t equals 0. Okay, and it turned out the way it was maybe it was back here somewhere, so it was negative. Okay, that doesn't actually give us the distance that the particle traveled, right? The distance that the particle traveled, it went back here, and then it went forward again. So if I wanted to find out what the distance, the total distance traveled, I'd have to figure out this distance, and then I'd have to add it to that distance. Okay? So let me just point that out here. Maybe I would write it, let's call, since the velocity is v, let's call the position s. We used to do that. So this is just s of 3 minus s of 0, this bit. This is your s of 3, right? So now if I want the displacement, I've got that. But if I want the distance traveled, I have to take into account the fact that half the time, or less than half the time, more than half the time, I'm going backwards. So then I would do, and I changed, we found, when do we change? We change where this velocity is 0, right? Where it crosses the axis. So clearly that's at 5/3, right? So I'm going to do the amount of time I'm going to travel forward, right? Absolute values. And then I'm going to add the amount of time I was traveling backwards. So that's how you would have to do it to find the distance traveled.